is its power to be able to interrogate the underlying components without breaking apart the energy storage and conversion system. The device has two electrodes. It has two connections. There's a positive terminal and a negative terminal. And all the ports you have, you don't have a window to look into it. You cannot break it apart that easily. In fact, as soon as you break it apart, it stops working. So the power of impedance spectroscopy is the fact that you can use those two points, those two contact points, the positive terminal and the negative terminal, and nothing else, to actually interrogate and slice and dice the components of the battery or the supercapacitor. So you can actually get independent information about the anode, the cathode, the separator, the electrolyte, and the interfaces between them without actually breaking apart anything. So that's why I think impedance spectroscopy is powerful. That's why I think it's an important technique to talk about. Now, the way it actually separates all these interfaces and all these materials is via time scales. Now, any impedance spectroscopy experiment, and this is sort of a conservative range, can go anywhere from 10 microhertz to 1 megahertz or 10 megahertz. And if you think about it, if you invert that, that's events as fast as microseconds and as slow as days. And the 10 microhertz is generally not limited by instrumentation, it's limited by your patience or the lifetime of your device. So you can actually, within the same experiment, within the single data set, you can interrogate events that are as fast as microseconds or as slow as hours to days. Which is important because a lot of these energy storage and conversion devices do have events that are going on in the microsecond, millisecond time scale in addition to day time scale. Its power lies in this bullet number 3. It can be done on the device under test without any additional probes. The way it's done is it's a measure of impedance, which is essentially a resistance measured in AC, and it follows simple Ohm's law. V over I equals Z. This is not different than Ohm's law, it's the same thing, it's just generalized to sine waves as opposed to DC levels. You can think of Ohm's law at impedance limit at zero frequency. Here is sort of the recipe for how these experiments are typically done. You find a fixed frequency, you find a fixed signal of amplitude, a fixed amplitude of AC signal. Then you choose your frequency, measure the impedance at that frequency, and then switch to the next frequency. And you scan the entire range of frequencies that you're interested in. And this is what it typically looks like, right? You apply a voltage that's oscillating as a sine wave, you get a current that's oscillating in response to that. You can plot it either as functions of time that are shown up here, or plot current versus voltage, and both of those plots have value in them. But in the end, you don't store this entire set, you only store the summary of this, which is V versus, which is Z. Now the reason I like showing this is because this to me explains why impedance is always expressed in complex numbers. Whenever you look at impedance, there are always two numbers. It's either real and imaginary or modulus and phase. Now the reason for this is because you have a sine wave. To explain a sine wave, you need two things, which is, one of them is amplitude, but the other one is phase, right? This starts at 0 and ends at 0, but this one is shifted a little bit. So you need to explain that shift in addition to this amplitude. If you look at this ellipse, you need to explain the slope, but you also need to explain this width. So that's why you need two numbers, and a great mathematical tool to handle number pairs is complex numbers. So we use complex numbers not because there's anything imaginary with impedance. We use complex numbers because it's a great mathematical tool to handle pairs of numbers. In the end, we generate plots like this. We either plot modulus and phase as a function of frequency, the polar form of complex numbers, or plot imaginary versus real, the Cartesian form of complex numbers. So They're all the same number, it's just looking at it in different ways. This one has to be logarithmic, otherwise you don't see anything. This one is generally plotted linear, so there's some value in looking at the data in a logarithmic scale versus a linear scale, so on and so forth. Now, everything I've said up to here had nothing to do with chemistry, had nothing to do with electrochemistry, it was all electrical. And the reason electrochemists are interested in this is because there's a great parallel in any electrochemical interface to a simple circuit. Now, in any electrochemical interface, what do we have? We have two phases, let's say a solid electrode and an electrolyte. And on that phase, on those two phases, we have an interface that we are going to do electrochemistry on. Now, let's think about that as these, sorry for the colors, but these are supposed to be purple and these are blue. So the blue ones are solids, purples are anions, and reds are cations. And this green circle is supposed to be an electroactive molecule that we are going to do some reduction or oxidation on. So we have applied some potential, and due to that potential, the anions came and formed a layer right on top of the electrode surface. Now, this is because there's some charge accumulation on the electrode surface, on the electrode phase. This is what's known as the electrochemical double layer. And from Physics 102, or whatever the code may be in your respective institutions, we know that this looks like a parallel plate capacitor. We have two layers of opposite charges that are separated by dielectric. Now, the dielectric here is the fact that that's an interface. We don't technically have a dielectric there. We just have those charges separated and they don't cross because the potential isn't right. So we have these charges on the electrode, charges from the electrolyte that center right on the surface of the electrode. And this is what we call the electrochemical double layer. And in order to model that, a true parallel plate capacitor is something that is very logical to do because it looks exactly like a parallel plate capacitor. There is a big difference, and we're going to talk about this in a little later, is the fact that there is no dielectric and this distance is very short. In typical electrolyte concentrations, 0.1 molar or above, this distance is less than a nanometer. And if you remember your formula for parallel plate capacitance, it's epsilon times A divided by D. So the smaller that distance, the larger the capacitance. So this electrochemical double layer is actually a very large capacitance per unit area. And that is the basis for things known as ultracapacitors or electrochemical double layer capacitors. They are very efficient because this distance is very short. Now, the reason we are doing this interface is because we want to do electrochemistry in it. So at some point, one of these charges is going to hop on, or it's going to pull an electron from the electroactive molecule. And that is the process I want to study. I'm an electrochemist. I want to understand the electrochemistry of certain molecules. Now, this process, we generally model with a resistor. Not because a resistor is a good model for it, but because we don't know any better. Now, the kinetics of electrochemical reactions can get very complicated. And there are plenty of theories, including Marcus and Butler-Volmer and all of the rest, to explain those. But what we do is we do what any physicist does whenever they're confronted with a nonlinear problem. We zoom in, we look at small amplitudes, and we call it linear. So anything nonlinear can be magnified enough to make it linear. And that's what we do by putting a resistor here. And then there's another resistance here, and this resistance we generally say is the electrolyte resistance, but it's there to essentially catch everything that we cannot explain. It's there to catch contact resistances, it's there to catch electrolyte resistance, it's there to catch any resistance that is not explained by these two. We are really interested in these two. This has to be there because there's extra resistance that we cannot get rid of. So combining those is what's known as the simplified Randall cell. It's simplified because it is grossly overestimating one very important parameter, and that is how you get this material to the electrode surface. So it's completely ignoring any transport. And I'm going to talk a little bit about transport, but not much. But ignoring transport, this is the cell that explains it. So if I can do some electrical measurement, namely impedance spectroscopy, and if I can use that impedance spectroscopy to extract the parameters of these components, I can extract the parameters of my interface. And if the two interfaces are modeled differently and separately in this equivalent circuit, then I can use that to understand my two interfaces separately from each other. So the reason they are separated, the reason that these two get separated is because a resistor doesn't introduce any phase shift and a capacitor does. So when you have a capacitance, your current and voltage are offset from each other in time, but if you have only a resistor, your current and voltage are on top of each other. So if you look at the typical semicircle, the reason there's a semicircle is because at high frequency, this capacitor is a short, so you go through this path and you only get this resistance. At low frequency, this capacitor is an open, and when that's open, you get the sum of these two resistances. And in the middle, you get something that is having a imaginary component due to the capacitance, and that's this bit right here. So by doing that experiment, you can identify all three components independently from each other. Now, here is first bit of how to avoid abuse. Now, one of the things you see in impedance spectroscopy quite often is because we want to do very, very long experiments, we want to look for experiments that takes days. A typical self-discharge measurement for a supercapacitor takes about 72 hours. And stability of samples that we cook up in the lab are always suspect. So we need a mathematical tool that tells us if our system was stable throughout my measurement. Now, a mathematical tool here comes from the optics world that they use routinely, that's adopted to the electrochemical impedance literature. So the three conditions that this mathematical tool checks are linearity, and that's also important because we know it's nonlinear, we just zoom in to make it look like linear. Stability, which is a very important parameter for long experiments, and causality. And causality is just there because it is possible that you're only measuring noise. What causality means is that the current you're measuring has to be due to the voltage you're applying. If you turn off that voltage and if that current is still there, that means that current is not causal. So this tool called Kramer's-Kronig actually checks for all three. Now the way it does it is by a complicated mathematical relationship here. It looks complicated, but the simple but wordy version of restating these equations is all it says is if you have a complex quantity, if you take the real part and do some magic math to it, you get the imaginary part. And if you have the imaginary part and do some magic math to it, you get the real part. And this has to be true. All it says is that the real part and the imaginary part cannot be independent of each other. They have to be able to get converted to each other. The problem with doing this transform is you need the entire frequency set, going all the way to infinite frequency and minus infinite because things are symmetric. Now, we do some mathematical trick to approximate it. We don't actually do the full transform, but we look into other methods of checking this. I'm not going to go into the detail of how this is done, but ultimately, when things work, they do work. The Kramer's-Kronig transform looks like this, and when things don't work, they really don't work. So this one right here is some data that I took, and it's clear that the Kramer's-Kronig transform did not work. So this is either nonlinear, non-stable, or non-causal. How do I check it? Well, this was done with 1 millivolt AC amplitude. So I said, all right, the next experiment is to go to lower AC amplitude. So going to 0.1 did not work. So the previous data was nonlinear because the amplitude was too high for this particular sample. Now in the impedance spectroscopy textbooks or beginner literature, you will always see that people say 10 millivolts is the magic amplitude to use, and it never is. Here 1 millivolt was too much and 0.1 was the right amplitude. I've seen samples where 1 volt is good enough. So you have to get your sample to tell you what amplitude you need to use. Here's another data set. This is not something I took, but this was sent to me as I was working for an instrumentation company for help. And I, unfortunately, and I'm sort of sad to say this, but I spent a couple hours on this data before looking at the Kramer-Skornik transform. And the Kramer-Skornik transform is bad. So this data cannot be fit to any equivalent circuit model because it's Kramer-Skornik not transformable. It turns out this was actually a paint coating on some metal, and the paint coating broke down in the middle of the experiment. So the impedance was rising, and then it broke down, and the impedance started coming down. So there's no way to fit this data. This is not going to fit to anything because this is not stable. What that means is that the sample that was measured at this frequency is not the same sample that was measured at this frequency. So the data here is not belong to the same sample that was here. So there's no way of fixing this. You need to either get your sample to be more stable or find a way to do the experiment faster. Alright, now, we said that we use a capacitor to model the double layer, and that assumes that you have a perfect surface. Now the only time I've ever seen a capacitor to be perfectly adequate for the double layer is a mercury electrode. Because in a mercury electrode your surface is atomically smooth, and so is your double layer. In any other case, you have defects, grain boundaries, different crystal facets. You never have a perfect capacitor. Now, in order to model this, the electrochemists actually developed an element that we call constant phase element. Notice it's constant phase, but not 90-degree phase. And mathematically, we introduced this exponent A to this I omega term. So if that A is 1, this is a perfect capacitor. And that A is generally less than 1. In the Nyquist plot, this is a true capacitor, this is a constant phase element. So instead of it being perfectly vertical, it's now slanted a little bit. Now, the constant phase element has been a component that we always use in impedance spectroscopy fitting, and everybody keeps using it because otherwise our data doesn't fit. But it's always been a contentious issue. It's always speculated that it's a fudge factor, we don't understand it, and so on and so forth. So as late as 2016, there was huge arguments and debates about what this is and how this is done. So I'm going to show you two schools of thought on it, coming from two very different experiments. In one of them, this is from the group of Vincent Vidier in Paris. What they do is they do localized EIS measurements. They have a surface and they come with a probe and they scan this probe, measuring the impedance across this interface along the sample. Now the point is that they have a reference electrode here and a counter electrode somewhere. And as they move their probe close to or far away from the counter electrode, they are seeing that the capacitance is constant, but the resistance changes. And the resistance changes just simply from the distance. And what they're saying is that it's this distribution of the resistances that's leading to a distribution of time constants that's leading to a constant phase element behavior. And what they are saying is as soon as you have a non-symmetric geometry in the cell, as soon as part of your working electrode is closer to the counter than the others, you're going to see this. Now the counter argument to he does very, very careful experiments, cleaning his electrode and cleaning his solutions. And for those of you familiar with electrochemistry, this CV should say a lot. This is polycrystalline platinum in sulfuric acid. And the fact that there's a small peak here and there are two peaks right here tells you that this is a super clean surface. You don't see those features, you don't resolve those features if the surface is not super clean. As soon as those are clean enough, he is saying that the exponent comes very close to 1, 0.992. And he's saying this is true for large electrodes, symmetric counter-electrode geometry, asymmetric counter-electrode geometry, whatever. So the use of constant phase elements are ubiquitous, we all do it, but the reason for constant phase element is not that well understood. Although there are people who claim that it's well understood. Okay, so the other thing about modeling is you keep seeing inductances thrown around. I am yet to see an inductance at high frequency that belongs to a sample. It's always belonging to some cabling. However, there is actually information in the low frequency inductance, and that's generally due to an absorption-desorption phenomena, but those are rare. Now that was a 25-minute intro on impedance spectroscopy, probably the fastest I've ever given. Now I'm going to go into examples. Case study 1, conducting polymers. Now these are studies from my own career that I've conducted over the years, and I'm going to give you a personal story on how I developed sort of my working principles. During my PhD years, I was trying to understand behaviors of conducting polymers, and if anybody here has done electrochemistry on conducting polymers, you would know that as soon as you start doping them or oxidizing them, you not only change their conductivity, but you also change their dielectric constant, and hence the current you are seeing is this compound current between redox current and capacitive current, and it's quite impossible to decouple those. I thought one could use impedance spectroscopy to decouple them, and started reading literature on impedance spectroscopy on conducting polymers. And here's a short list of the various circuit models that people have used in order to model these. And I'm not exaggerating when I say this is a short list. There's probably 10 times more than what I'm showing here. And all of these are completely orthogonal to each other. So this was very frustrating because I did not know what to do. So I developed my own model and worked on trying to identify physical processes that can couple two components in my model. So I've isolated the Faraday part from the transport part, and I've isolated the surface from the bulk. And using this, I was able to develop a method that can decouple Faraday current, which is the total redox current, from the capacitive current, which is just the charging of the capacitor. Now this is important because what you want to do here is you want to go back and say, I've oxidized my material with that many electrons per monomer if I am at whatever potential. Now in order to do that, you need to know the total Faraday current that was passing through your system. And you need to isolate that from the total capacitive current in the system, but the capacitance is not constant. So that's why what happens is when it's in the reduced form, the capacitance is low. As it's getting oxidized, the capacitance starts going high. And then, once the oxidation starts dying down, the capacitance is roughly constant. It's rising a little more because of the coherence length distribution of these things. And these are two different polymers. This is P dot, this is polythiophene, and they both show similar behavior. The next story I'm going to quickly go through is dye-sensitized solar cells, and that's one that's very related to energy storage and conversion. For those of you who don't know, dye-sensitized solar cells, also known as third-generation solar cells, and third generation is generally defined as anything that's not first or second. That's literally how they define it. It's not my definition. So the way these things work is they get the light from the back end of some porous titanium into a die, and that die gets excited, and that excited electron hops onto titanium, which is an electron conductor, and hops through the titanium to the outside circuit. And on the other side, you have some redox couple, generally iodide, triiodide, that does the other part of the reaction and completes the circuit. The advantage of this type of solar cell is because you have a dye molecule, you can tune the absorbance. In semiconductor solar cells, you're bound by the band gap. You cannot absorb anything lower than the band gap because your material doesn't absorb there. By using the dye here, you can do chemistry to tune what part of the spectrum this absorbs, and you can actually make dye-sensitized solar cells work even on cloudy days, because they can work with the green and the red part of the spectrum in addition to the UV and the violet. So these are probably not that useful in Central Africa, but they are pretty useful in places like Arnhem, where you don't have any non-cloudy days. So because of this many interfaces, there's the titanium, there's the dye, and there's the counter-electrode. The impedance spectroscopy of these things are very rich. Here is some typical data, and you see that the data has quite a number of kinks and turns and bumps. The typical model in the literature for this is this. Now I'm going to skip the details of the model for now. I'm only going to say that this is a 15-parameter model. And though the data is rich, I don't know that there are 15 degrees of freedom there. I don't know that I would trust a 15-parameter fit, even if the data is this rich. So, I am missing this one. Sorry about that. What I've done is I did this fit, and then I took this exact same cell, and I've done X-ray measurements. Turns out you can actually optically measure things like recombination rate and charge extraction rate. And those correlate to various R's and C's within this model. So the only way I could trust the fit here was by verifying the parameters with independent measurements. So impedance spectroscopy is powerful because all of these bumps actually represent different interfaces in the system. But which one represents which interface is one issue. And there are probably 20 ways to fit this to this data. So identifying the correct set of parameters is an issue that needs to be tackled. Alright, so let's go to talking about batteries and supercaps. Now the rest of this talk is going to talk about battery impedance. And I'm going to be talking about two samples in general. The two samples, one of them is a nickel cadmium, and the other one is a lithium iron phosphate. Those are just commercial batteries that I bought off the shelf, and I've measured and analyzed. So the first parameter that, when you look at any spec sheet of a battery, you see is something that's known with different names, but all are the same thing. Battery scientists call it internal resistance. The fuel cell folks call it HFR, high frequency resistance. And the supercap people call it ESR, equivalent series resistance. They are all the same thing. It is that catch-all resistance that I was talking about. Contact resistances, electrolyte resistance, everything that you cannot account for by just explaining the interfaces. So that actually is the easiest number to obtain. All you need to do is you need to look at the high frequency intercept with the real axis. So for the lithium-ion cell, it's right here, so it's about 30 milliohm. For the NiCad, it's about here, so it's about 25 milliohm. So that number, you don't even have to do any fitting to extract. You can just look at the data and grab it. That's how you do it on the Nyquist. If you want to do it on the body, it's just the lowest number that you see on the Z-mod axis. That is your equivalent series resistance. All Alright, so let's take a closer look at the whole spectrum of the lithium-ion cell. Now the cell, these are all the same data, by the way, I just zoomed in differently. So clearly there is plenty of information in this data. And I assure you that all of these are real, repeatable, they are not noise, they are data. So there's at least 2 semicircles here, if not more. There's actually a 45-degree portion here, and there's possibly another portion here, and then there's a vertical rise. So the interfaces on any energy storage and conversion device, if I look at it at a very large block diagram level, looks like this, right? We have current collectors for the anode and the cathode. We have the anode active material and the cathode active material. Then we have some separator membrane electrolyte depending on what the device is and what it's used for. And in all of them, there's actually an interface. There's a current collector active material interface. There's the active material separator interface. Separator electrolyte has its own resistance and dielectric properties, and the same thing happens on the cathode as well. Alright, the one issue here is porosity. Porosity is great in order to make efficient use of materials, but it's horrible in terms of impedance spectroscopy. It's useful because you want high surface area per volume, you want high surface area per gram, but the reason it's horrible for impedance spectroscopy is sort of illustrated here. At every point on that electrode surface along a core, you have a different impedance. You have a different resistance to the bulk, you potentially have a different capacitance because the chemistry within that area might be different, and you are measuring the whole thing. You are getting the integral of this whole thing. So you have to step back and try to analyze what this looks like. So this is the simplest porous electrode that I can find. It's a supercap, and this is what the data looks like. And if you try to fit it with sort of standard elements like your R and C, you capture the bulk, but you notice that there's actually a transition that you miss. And the reason you miss it is because there's a distribution of these R's and C's that your model does not have. Your model only has one R and one C, but the data has a distribution of it. So you have to resort to math to actually be able to grab that distribution of time constants. And you have to think of infinitesimal R's and C's and then integrate them under certain conditions, and your fit goes from this to that. So as soon as you take into account the distribution of time constants properly, now you can start to fit the details. Now using transmission lines are really not that straightforward, and this is probably the only case I know of where it fits perfectly. Now, let me skip these. Alright, so these interfaces are certainly transmission lines. That's where my active material meets my electrolyte. So right at that interface I have porous electrodes, and I know I have porous electrodes on both sides most of the time. So I need to put transmission lines on both sides. Now using that model, I can actually fit this entire data set. And that fit is perfect. The only place it is not perfect is down here, but I don't care about that part because that's due to cable. That's not due to my sample, that's due to an artifact, that's just the cable inductance, so I don't care about that part. The parts I care about are all of these features, and all of those features are actually grabbed by my model. Now, notice I've been pretty vague about how I connect these. I put them sort of over there. I said each and every interface has its own R and C, but I did not say anything about how these come together. Now the reason I didn't say anything about how they come together is because I can combine them in lots of different ways. For this one I've combined them this way and did the fit, but I could have combined them in 20 different ways, and the reason lies in one of the slides that I skipped that I'm going to go back to. Sorry, right here. Now the problem is, impedance spectroscopy by itself is not able to distinguish between certain elements or certain circuit geometries. These two, for example, they look like they are completely different circuits, and they are. But to the impedance spectroscopy measurement, to the EIS data, they are completely identical. There is an analytical equation that you can write from this to here. For different capacitor and resistor values, these two give you the exact same impedance spectrum. So just by impedance spectroscopy, you cannot distinguish between these two circuits. Now, as soon as you go to 3 time constants, life gets even more complicated. You have all of these circuits that are completely indistinguishable from each other. So with that many components, how to combine them becomes a problem. The way to solve that issue is to actually do independent other experiments. Just by impedance spectroscopy, you cannot solve it. Unfortunately, that's the nature of the beast. So using impedance spectroscopy to distinguish this and that is what I would call abuse. Because impedance spectroscopy does not have that power. These two are indistinguishable. So you need to either do different experiments to find out what interface belongs to what, or somehow know your system enough to decide how these are connected. So let me go back to where I was. All right. Now I fit the lithium-ion cell. Let's go back and try to fit the nickel-cadmium cell. Now I could have used the exact same model to fit the nickel-cadmium cell, but the nickel-cadmium beta does not have that many kinks or bumps. It has much less information. So I fit it with a much smaller model. And the reason I fit it with a much smaller model is because I do not want multi-valued numbers. So this is the smallest model that could fit that data. And here's what the fit looks like. And I could extract information out of here that I could not extract in the lithium-ion data. The biggest difference here is the fact that this nickel-cadmium actually has a horrible self-discharge, and the lithium-ion did not. So the fact that this semicircle closes, whereas this one didn't, this large one didn't, has to do with the self-discharge. And the nickel-cadmium, because it had a horrible self-discharge, I could resolve a different feature, but that ended up hiding a lot of the other features that I could resolve in the lithium-ion. All right. Now, I'm going to talk about one last thing before I finish here, and that's some of our more recent work that we've done within the last year. Now, this work is about a very real problem. The problem is a lot of people want to design electric cars, electric airplanes, electric motorboats, electric superbikes, and when you are designing them, you need to choose and decide on a battery to use before you actually build the device. So it's hard to test each and every battery, and you cannot test it once it's already built. So one needs to be able to predict what the voltage of the battery is going to do throughout its discharge cycle. So given an arbitrary discharge profile, and use a very small subset of these discharge profiles. And when I say arbitrary discharge profile, I mean arbitrary. And these discharge profiles can be very different depending on if you're using a cell phone, if you're using a car, if you're using an airplane. And even for cars, there are tens of different discharge profiles. An urban drive schedule is very different than a highway drive schedule, and all of those are published by the EPA. And in fact, they are published for different cities. This right here is the Istanbul drive cycle. There's actually a New York drive cycle, in London and Paris, and whatever you want. That's a GSM discharge profile. It turns out that cell phones don't draw much power when they're idle, but as soon as somebody tries to call you, there are these spikes in current that go to about somewhere about 8 or 9 times the idle current. So just knowing the capacity of the battery does not help you resolve these issues. You know the discharge is going to be 2 amp hours total, but you do not know how the battery is going to react to a spike. And there are lots of different energy storage systems. In fact, I've just shown 3 types of batteries here. This is a power tool, power drill battery pack based on implemented light rides. Here is a submarine battery pack. And does anyone know what chemistry submarine batteries use? And I'm talking about nuclear submarines. What's that?
Hydrogen cell?
Mm-hmm. Does anybody know why submarines don't tip over? How do they stay upright? They are this circular thing, right? And there's actually added weight on top, so it should be easy to tip. The reason they don't tip is they have something very heavy at the base. They put a very, very heavy load at the bottom of the submarine. And the very, very heavy thing that keeps them upright is the battery. But what's the heaviest battery we know? Heaviest, safest? All of us use it. Lead. It is lead acid. Even the most expensive, most advanced nuclear submarine uses lead acid batteries. And the reason they do not switch is twofold. One, they want something heavy, because that's what keeps the submarine upright. And two, they want something safe. The last thing you want to deal with when you're that many meters underwater is a battery fire. So they are still using lead acids even in the latest technology. So this actually is the picture of the top of a submarine battery pack. This is a battery that UASA manufactures for space applications. So this can, along with the contents of it, is supposedly going up to space, and it is going to be resistant to all the cosmic radiation and low temperature and zero pressure and all of that. And here's the supercap from Maxwell Technologies. And supercaps, though they don't seem to get much attention, they are actually used very heavily for things like braking on wind turbines for electricity when the wind is too heavy, or things like acceleration assist in cars when they want to turn off the alternator for a little bit to give the engine a little more kick, for actually helping train locomotives accelerate. So they are not good for longevity, but they are good for high power for short time. So the holy grail of this work is, given one of these and one of these, can we predict what the voltage is going to do throughout this discharge? So we are not the first ones to look into this. Of course, people have looked into this. And I grouped the literature here into 2. There are the first principles guys. They start from first principles. They take each and every interface and they solve the kinetic and transport equations for each and every interface, and in the end they predict voltage. Now, though this is great, the problem is you need the parameters for each and every interface. You need the dielectric constants, you need the kinetics, you need the diffusion coefficients, and generally you don't have those. The second portion is the equivalent circuit guys, and the way they do this is they sort of simulate the battery with some equivalent circuit. And those equivalent circuits are typically very, very simple. And the reason they are simple is because they have to be. Because as soon as they are not simple, actually using them in a DC spice model is quite impossible. So without simplification, you cannot do the math to go from frequency domain to time domain. And plenty of people have attempted, including myself, to do this. And it's really not straightforward. As soon as you go to a model like this is the frequency domain response in the complex domain. Taking this to time domain is quite impossible. So here is what we had proposed last year, and we've shown that it works. So the ultimate goal is using this to predict that. The way we do it is, instead of trying to cross this arrow, which is hard and complicated, we move the problem into frequency domain. We measure the impedance in the frequency domain. So we take the current versus time, Fourier transform it to a current versus frequency, and then we can measure impedance versus frequency. And at that point, it's just a simple complex multiplication. So I multiply them, and I have a voltage as a function of frequency. And then I can inverse transform it back to time domain. So instead of trying to do the math here, instead of trying to take this measurement and bring it over to time domain, I take the model and bring it over to frequency domain. Now, does this work? We use different profiles, very slow, highway drive, sort of a little bit fast, but not that much. And this is an urban drive schedule that oscillates quite a lot. And we use 3 different battery chemistries and 1 supercap. And in all cases, this actually does work. So what I'm showing here is an array of 3 different energy storage systems, 3 different discharge profiles, and in all of these panels, what I have is, with the red, I'm showing the measured voltage, and with the blue, I'm showing the predicted voltage. So the measured and the predicted agree quite well, and I am going to zoom into a couple of them. So this is the highway drive schedule on the supercap. And you can see the red is what I've measured afterwards, and blue is what I've predicted it to be. Here's another one. This is the urban drive schedule on the nickel metal hydride. Again, it just works. Now, we could not do this on the nickel cadmium, and I'm going to tell you why. The reason we couldn't do it is something that I've already told you as I was talking about the nickel cadmium cell before. It has a lot of self-discharge. And one thing I've not included into this model is self-discharge yet. So modeling self-discharge is something I'm looking into, but we don't have it in here yet. But for now, here are sort of the maximum errors on all of these. So in all cases, it's less than 1%. In fact, in certain cases, it's much less than 1%. So we're pretty happy with these results, and we are using impedance spectroscopy here in a way that wasn't used before. We are using impedance spectroscopy without any fits, without any free parameters. We are using the data as is. We are not touching it. We are just using impedance spectroscopy to predict time domain results. All right. The last thing I want to show is these two. Now, everything I've said about impedance spectroscopy basics are covered in one or both of these books. The one on the left by Barsuko and McDonald is great if you're mathematically oriented. It's very brutal otherwise. If you're less mathematically oriented, I would recommend the book by Orozman Tribole, which is the one on the right. And that actually has a good 2 chapters in the beginning that's giving you the math that is necessary to follow the rest of the book. And just to introduce the characters, Barsuko right now works for TI, Texas Instruments, and their battery division. And he is the person behind all of their battery state of charge, state of health prediction algorithms. He is the person behind our cell phones being better at telling us what % of battery life is left. McDonald is now retired. He was a solid-state chemistry professor at North Carolina. Orazem is from University of Florida. Tribole is from Paris. to material properties. And AAA is part of the group that does that localized impedance work. So all of these are relevant characters, and the books are pretty good. So that's all I have to say. I'm happy to take any questions.
Those impedance measurements, are they collected under isothermal stability or?
Right. Okay, so for batteries, the way these are done,
because this is a common problem in discharge.
It sure is. So the data that I have shown, let me get over here. Right. So this data, I had to take not just under isothermal conditions, but also isopotential conditions. I had to control the potential and keep it in a thermostatic environment. Now, because of the way I measure these, I'm not actually discharging them. I'm not putting any DC current on them. It's just AC current. So the state of charge doesn't change, so it doesn't heat up that much. But if I do this under current control, the smallest offset is enough to discharge it slightly and ruin my measurement.
This is cycle or?
Right, so this measurement is done all the way down to 1 microhertz. And 1 microhertz is 1 million seconds, which is close to 12 days or so. And I have to do that for 3 cycles. So this measurement was about a couple of months. And I had to keep my battery stable for a couple of months. So I did it at constant potential in a thermostatic environment.
For Nanoscience, we have different layers. So how can we calculate the interfacial charges of different layers, and how can we say that this capacitance shows this interfacial charge?
You're talking about like a photovoltaic P3HT PCBM type cell, right? Okay. First, it's hard to say that you can always calculate it. But in cases where you can calculate it, you need a difference in time constants. One interface has to respond in the millisecond time scale, the other one has to respond in the second time scale. As soon as they're different, then in the impedance data you're going to see features like this, because they're going to be resolved in time scale. When you're doing a 1 megahertz experiment, both of them are going to be ignored. When you're doing 1 kilohertz experiment, one of them is going to be ignored. And when you're doing 1 hertz experiment, both of them is going to be there, and you can't decouple them. In terms of assigning which part belongs to which part in your cell, impedance spectroscopy cannot do that. Because all you can do is you can say there's one component here that's faster than the other. But you need another experiment or theoretical knowledge from wherever to tell you which one is the faster one and which one is the slower one. In terms of calculating the charge density, that is only possible if you also know the dielectric properties. You know, this is only going to give you a capacitance. To go from capacitance to charge density is another step.